Now, welcome everybody. It's great to have you here. If I could have your attention for I will not keep you long, I promise. Now, we are here in this beautiful location in Petten, and we are here to discuss how to make dimethyl ether in a sustainable way. And my colleagues from TNO are gonna show you the installation that we have built, and we are going to have a program this afternoon to introduce you to the topic, but also to introduce you to the consortium, because this work has been part of a project called Electrons to Chemicals. It is sponsored by many parties. One of the parties is Interreg, but there are also other sponsors that believed in this project, that believed in making chemicals in a sustainable way. So in the next few minutes, I would like to tell you a few things about the bigger project, and that will give you the context for the workshop that we have today. It doesn't go to the next slide. I will need your help, Erin. I don't seem to be able to go to the next slide. Not sure? Oh, yes, thank you. Okay. In this project, we have the ambition of making this connection between the energy sector and mainly the renewable production of electricity and the chemical sector. So to use renewable electricity to make chemicals. For this, we chose two separate lines to address in the project. One that is going to be presented today. It's to make dimethyl ether, and another one it's to valorize CO2 and electricity to make formic acid. And I hope to invite you to an event later this year to show you the progress that we have done there. Now, the partners that are working and have made possible the advancements that came here today to see are from this sea, the North Sea region, and you can see them here. The main objective of the project was indeed to stimulate and to support the companies to invest in this development and implementation of innovative power-to-X technologies, and to valorize the wind farms as well as the chemical clusters that are in this region. Now, we are here presenting the results of the project to you, and it is very important that that you realize what can be done in a sustainable manner and how to make, in this case, dimethyl ether, and how to collaborate with the partners that we have already in this consortium. The project itself has reached several goals. Here we are looking at the power-to-X, the flexible pilot for the production of dimethyl ether. But in order for this to be possible, we have also designed and built lifetime testing stations for both electrolysis of water as well as electrolysis of CO2. As I told you, for the other line, we are designing and building also another pilot for the valorization of CO2, and at the same time, we are doing feasibility studies for the implementation of these power-to-X technologies. So techno-economic evaluations, technology implementation plans, and as well as scenario modeling, and trying to see where and how can we add the most value to with our technologies in the existing industrial landscape. this gives you, I hope, a bit of a bigger view of where we are coming from. You are going to see today several talks from the project partners that have worked very hard to reach the results that we can present to you today. And before I go on, I would like to also point to you the host for us today. It's Erin Scholz. She has been organizing. She has organized the whole workshop, and she will be our contact point for further logistical issues. We are here with about 40 people, but you have to be aware there are also people online. Hello for the participants online. I hope you will have a great time in this workshop. Well, I will see you at the next coffee break and in the discussions. So I hope you'll enjoy.
Okay. I give this presentation about the strategy to design catalysts for direct synthesis of dimethyl ester from carbon dioxide. So because the catalyst is at the heart of this process. First slide, I just want brief information about our laboratory. So we are participating in this Interact project, and our laboratory is located in the northern France in Lille. It's about 300 kilometers from here. It's a mixed laboratory of CNRS, University of Lille, and Central Institute Engineering School. So we have about now 300 persons which are working in our laboratory. So PhD students, also permanent staff, so mostly professors, CNRS researchers like myself, also PhD students, administrative staff, and different interns. So, and the task of our laboratory, the main goal of our laboratory, it's design of catalyst and maybe process and chemistry for energy, environment, sustainable development. And in particular, myself, I work in the research group, which is called Catalysis for Energy Platform Molecules. And we are trying to develop the catalyst and so the process for energy relevant process. So, I think it's both. Okay. So this project is a part of, say, of power to gas technology. So the idea is to use carbon dioxide and sustainable hydrogen and to create sustainable fuel. So the green hydrogen, as it was explained in this introduction, is produced by electrolyzers, and we have captured CO2, and then we convert. Our gas technology convert CO2 to a gaseous fuel, such as methane, syngas, dimethyl ester. Dimethyl ester actually is the target of our work here, because we're converting CO2 and hydrogen to dimethyl ester with important sustainable fuel. Why we should produce dimethyl ester? So first we consider mostly dimethyl ester to use as a fuel, because it can be used in conventional diesel engine with modified injection. It's large potential market. High C10 number for diesel fuel, which is very important, quiet combustions, clean burning. If we want about distribution of dimethyl ester, we can use already LPG distribution system. So, and we produce very clean dimethyl ester without any impurity, in particular sulfur, so it can be considered as clean fuels. So, and also there already have been developed the trucks, especially trucks, which can use dimethyl ester as a fuel. So now about the reaction itself. So also synthesis of dimethyl ester is a part of, say, can be considered as a part of carbon cycle. So we can get CO2 from different plants, then convert CO2 to dimethyl ester, and then dimethyl ester can be combustion to CO2. So it can be this technology can be a part of carbon cycle for utilization of carbon dioxide. And if we talk about reaction itself, here there are the major reactions which occur during dimethyl ester synthesis from CO2. So there are several reactions taking place. The most important one is synthesis of methanol, which is intermediate, the synthesis of dimethyl ester from carbon dioxide. Methanol can be obtained from CO. CO2 can be obtained also from CO. Then the second important reaction is the dehydration of dimethyl ester, of methanol to dimethyl ester, which produce also dimethyl ester in water, and also another reaction which is also a part of the process is a reverse water gas shift reaction. So reaction of CO2 with hydrogen making CO in water. And what you can see on all this reaction, which is an important feature of all this reaction, so this whole reaction to some extent produce water. So I don't want to anticipate here the presentation of my colleague, but I will say that water is a product, and most of the reactions are limited by thermodynamics. So extraction of water can be interesting if you want to enhance this process. So here I show the reaction is limited by thermodynamics. So here I just put some thermodynamic data about CO2 conversion and dimethyl ester selectivity as a function of the most important parameters, such as temperature and pressure. So if you see first about conversion, so show this slide, you can see that if you want to obtain maximum conversion, which can be allowed by thermodynamics, we have to conduct reaction at lower temperature. However, the problem is that at lower temperature we are limited by kinetics. So the reaction rate can be zero, can be very low, can be even zero. So for that reason, we have to, to choose the optimum temperature which can be convenient for the reaction. You can see also some, say, maybe a little bit unexpected increase in conversion with high temperature. So this is due to so-called reverse water gas shift reaction, because in fact CO2 can be converted to methanol, dimethyl ester, also to CO. And if we increase the temperature to very high, more than 300 degrees, we have very significant conversion of CO2 to CO, which is not very desirable process for our reaction. So another important parameters is pressure. So when we increase pressure, it's generally favorable for methanol synthesis and dimethyl ester synthesis. So for that reason, the reaction is conducted under the pressure. So there are different points of view on the optimal pressure. I would say maybe about 50 bars will be kind of one of the optimal pressure for this process. And another important parameter is dimethyl ester selectivity. So you see that dimethyl ester selectivity, so thermodynamically, the highest dimethyl ester selectivity can be obtained at lower temperature. So, and we increase the temperature, we lose dimethyl ester selectivity, which can be due to competitive production of CO by reverse water gas shift. And also, thermodynamic doesn't allow us to obtain 100% selectivity at steady state condition. Do dimethyl ester even at say moderate temperature. We also have a thermodynamic equilibrium. We have significant amount of methanol. So I try to write it here. How was can see. So for that, I will just conclusions the message of the slide that one of the main challenge of this reaction of process dimethyl ester from CO2 is efficient management of thermodynamics of the process. Of course, we have catalysis because without catalyst, reaction doesn't take place. But if we want to optimize the process, we need to handle the operating parameters. Okay. So now I will take about the catalyst. So what the catalyst we have been developing for this process is so-called functional catalyst. You see that reaction involves several steps. The first step is synthesis of methanol, because methanol is in. For that, we use typically metallic catalyst, so for methanol synthesis, which is shown here. So this catalyst give us methanol, from CO and hydrogen. Also, it can give you reaction which we doesn't like very much. The worst reaction which you may have is make production of methane. Because methane is a byproduct, however, we don't know what to do with. We know what to do with the methane, but it's only combustion can be. So another byproduct is CO. CO, of course, it's not say the best product, but however, CO can be recycled because CO can be recycled, and the cycle can be converted to methanol in the second cycle. So it's bad. So also have production obviously of water. And then when we produce methanol, we have to dehydrate methanol. For that, we need another catalyst, and you can see it's acid-based catalyst, so acid component for dehydration of methanol. And what we can have on this, typically we have dimethyl ester at this condition of methanol synthesis. However, if we, for some reason, increase the temperature, we can switch to so-called methanol to hydrocarbon, methanol to olefins. There are different. It means they will produce hydrocarbons at high temperature, mostly hydrocarbons. So it's in terms of, if we use metal catalysts, we'll have mostly like paraffin, say propane, ethane, this butane, this kind of product. So which also, of course, are not the product which we like in the process of dimethyl ester synthesis. So for that, we have to design this catalyst. We have put them in interaction and to obtain the best result possible for this process. Of course, this catalyst, I will give you examples, of course, later on. So as this catalyst can interact together, and of course can, because you have to put catalysts together, there is interaction, chemical interaction between these two components. Okay. So now I talked about methanol catalyst, which we're considering. First, the most known catalyst for methanol synthesis is copper-based. However, it's not just pure copper. Pure copper is not the best catalyst, even better. So it could be copper zinc. Important is couple of copper and zinc oxide. It's very important for this catalyst. Without that, and also we have, say, support to say binder. Typically, is this common binder which I use is alumina, or can be zirconia used, maybe something else. So this is the most common catalyst, copper-based. And then now, if you see the literature for methanol synthesis from CO2, you find a huge number of publications during the last 10 years. So people try different systems. I would say the most common one is noble metal bimetallic catalyst. Here is palladium, which can be to some extent have properties similar to copper. Gold bimetallic catalyst, indium, so nickel catalyst. Another class of the catalyst which can be used for methanol synthesis is oxide catalyst. Here an example of zinc zirconia oxide, indium, gallium. So these oxides can be used, so they have maybe not so good performance at condition of methanol synthesis, but can be used for another application for another process when we produce methanol. And some papers about sulfide, that some sulfide catalysts, especially modified, not just about sulfide, but they have been modified, can also have good performance in methanol synthesis. So we did analysis of the literature, and so I wrote this paper, Nature Review, which will compare different class of catalysts and different ways, because methanol can be also produced by heterogeneous catalysis, as we do, can be produced by homogeneous catalysis, can be produced by enzymatic catalysis, by electrocatalysis, which now is kind of booming area, and by photocatalysis. So yes, there are different options to make it. So maybe some of them for short term, some of them for longer term. So it's different. So now just some data which we found here to compare different catalysts. So we see conversion and selectivity. Actually, you can see that if we want to produce methanol, there is clear trade-off between conversion and selectivity. So methanol selectivity is limited that we have a byproduct CO. So, and after say analysis of all literature, if you say under conditions of heterogeneous process, when we want to make methanol or maybe dimethyl ester, copper zinc catalyst remains the catalyst family par excellence. So it's the best, the most active catalyst which is available now. There are some reports about good performance on other catalysts, but sometimes it's very exotic system. Sometimes it's very difficult to reproduce. So that's why copper is the best. Copper zinc is the best. Is the most studied and also have high activity, high selectivity, and also economic advantages of this catalyst. So we typically, what is important is microstructure, metallic copper, zinc oxide. So and also we can obtain relatively high copper dispersion of the catalyst. So the surface area of metallic copper should be 18-23 meters per gram. And copper oxide particles, they interact with metallic copper. It's very important. I will show you, and they provide the synergy. So if you want to good catalyst, we should have copper and zinc oxide, which is interaction with this. So okay, now I will talk about acid component, because we need acid component for dehydration. So maybe the most simple one is amorphous oxide. I will say such as alumina, for example, which can provide some weak acidity for conversion of methanol to dimethyl ester. However, in our reaction, we produce some amount of water. And I say that maybe it's not, maybe some process can work, but alumina is usually sensitive to the presence of water. It's hydrophilic, so can form boiling, for example. So and this zoolite, the common zoolite ZSM5, SAPO 34, and also in this work we try kind of to use a new system of zoolite, embryonic zoolite, which kind of alternative acid component for this reaction. So here is the zoolite, so the ZSM5, I think many of you know, the ZSM5, SAPO 34. So this SAPO 34 has small pore and have weak acidity zoolite, and the ZSM5 is larger pore, so for SAPO the pore is 3.8 angstrom, for the ZSM5 5 angstrom, so in strong acidity, so medium or strong acidity, and SAPO and such have weak acidity. But it's normally sufficient to make dimethyl synthesis. And embryonic zoolite, what is embryonic zoolite? It means when we make synthesis of zoolite, we don't create complete organized structure of zoolite, we stay at some step of crystallization. So we have already formation of main fragments of zoolite, but we don't have very, well-organized crystals. And this has advantages for the catalysis, because for many reactions, even for dimethyl synthesis, a small pore of zoolites can be a problem, for example. So because it provides some diffusion limitation. So for that reason, using of embryonic zoolite can be interesting because we have larger pores. For example, here there is a picture of embryonic zoolite compared to ZSM5. So we can see that in embryonic zoolite, we have a lot of cavity, a lot of pore, mesopores, so it's usually convenient. Of course, the acidity is a little bit lower than conventional ZSM5 zoolite. However, it's can be interesting for a reaction which don't require very strong acidity like methanol dehydration. So this can be developed in collaboration with our colleague Professor Belkacem. So, and they have actually, if we tested this zoolite in CO conversion to dimethyl ester, and we found better conversion can be reached and also can reach higher selectivity to dimethyl ester. So now I will, in the next slide, I will try to summarize the main parameters which influence on structure performance correlation for this catalyst. So parameters of hybrid catalyst, because it's hybrid catalyst is functional with two components. So, and first, for example, here, one of the parameters which affects the activity of this catalyst is copper dispersion, means the size of copper nanoparticles. So if we have, for example, copper zinc catalyst, so on alumina, zirconia, ceria, if it's in terms of acid reducibility, here there is TPR data which characterize the acidity of copper. It means consumption of hydrogen during heating of the catalyst to hydrogen. They are pretty similar. However, you see that the conversion will be different. So this is a free catalyst. And what we found, we compared with the copper dispersion measured by XPS. And what we found, if we have better copper dispersion, in most cases, it results in higher activity of the catalyst. So the first parameters in the catalyst which need to be controlled is copper dispersion. And this observes a different temperature. The second parameters is, I say, bimetallic catalyst. So what we say, bimetallic particles. For example, here, it was a catalyst which we designed is copper palladium catalyst. Different copper palladium catalyst, so they have different activity. So, and what is also important, you can see here the selectivity. The useful product, I would say, is that the hydrocarbon products oxygenate, like methane, methanol, dimethyl ester. What you can see, for example, if I take just monometallic catalyst, palladium-based catalyst, which is considered a good catalyst methanol synthesis, and mix it with zoolite. So this is a hybrid catalyst. On this catalyst will produce mostly methane. So it means if we use palladium catalyst monometallic, it's not good for this reaction. We almost don't have any dimethyl ester. If we use just pure copper catalyst, what I say, pure copper catalyst without zinc, we put, let's say, on alumina, we mix with zoolite, ZSM5, and then we'll see what happens. So what we obtain here, it's I can't show, but it's a lot of products, also a significant production of methane. So it means that pure copper catalyst is not a good one. So it's not good because it gives methane, which is completely useless for this process. And when we have mixed so catalyst, copper palladium catalyst with different composition, we produce the main product on this catalyst is methanol and dimethyl ester. So in fact, you need this bimetallic species for production of methanol dimethyl ester. And we did analysis by microscopy, and we see in this catalyst when we have good selectivity to methanol dimethyl ester, we always have bimetallic nanoparticles copper and palladium. The same is true for when we have copper zinc. This is oxide, because always copper itself, just my message, copper itself doesn't a good catalyst for methanol synthesis and dimethyl ester synthesis. So we need to create this synergy. Then another parameter is acidity. So here, if you don't have any acid component in the catalyst, you make only dimethyl methanol. There is no dehydration. So for that, you need some I would say acid component. So here we use Sapa 34 in this catalyst. So it's copper alumina catalyst on mixed with Sapa 34. So, and we see we change the ratio between methanol synthesis and the acid component, and so between 1 and 5. So, and what happens actually? Because we thought that acidity plays a major role. Apparently not. Apparently you need some acid site, but the amount of acid site is not kind of very, very important for dehydration. Because in all cases, in this case, we're significant extent limited also by thermodynamic limitation. However, if we play the ratio between methanol and synthesis component and acid component, we can increase only slightly the selectivity to dimethyl ester. So it means that in fact, when we don't have acid site, we don't have dimethyl ester. However, when we have only a small amount of acid site, we produce dimethyl ester. However, as I said, because of thermodynamic limitation, we cannot obtain only dimethyl ester from CO2. Under this condition, we always have some amount of methanol. So now, what I was talking about, the interaction between two components. Here it's just example which I give you. It's copper palladium catalyst. So the first we studied reducibility, because palladium is noble metal, easy to reduce. However, copper, of course, it can also reduce, but reducibility of copper is difficult, more difficult than palladium. And when we have here's an example of TPR, so we reduce the catalyst with hydrogen and see at which temperatures hydrogen is consumed for the reduction. So, and what you can see, if you use palladium catalyst, it's reduced 100 degrees. So it's looking, but it's not so. So it's PDL, so it reduces 110, 146 degrees. And if you put copper, the copper is reduced under these conditions to 285 degrees. So we have 100, say more than 100 degrees difference between the temperature needed for reduction of copper and palladium. When you have mixed catalyst, bimetallic, so you have kind of intermediate value of the temperature needed for the reduction. So, and then we also measured acidity when we mix two catalysts and then combine them at high temperature. So, and to see what happens with the acidity, in fact. And what we found that acidity decreases when we mix. If acidity calculated the amount of zeolite in the catalyst, acidity decreases when we consign the temperature at the catalyst at high temperature. And you cannot see very well, but you can see on this bottom part that there is a number of Bronsted and Lewis site in the zeolite, in pure zeolite, in copper catalyst, and in bimetallic catalyst. What actually happens when we mix in the mixed copper palladium catalyst, the decrease of the we can see decrease of the in the number of Bronsted acid site after mixing methanol synthesis component and zeolite, and this decrease was more significant for pure copper catalyst, which is difficult to reduce. And we didn't observe this effect in decreasing the acidity in palladium catalyst, which is the most easy to reduce. So this actually views that copper, which is difficult to reduce, can migrate inside the zeolite as cationic species and decrease to some amount, react with acid site and decrease the amount of acid site and the zeolite. So what we see that we didn't see migration of palladium however, we could see the migration of copper, and in the mixed catalyst, of course, it depends how much copper we have, how much palladium we have. So there is indeed, there is an entire catalyst, there's always interaction between two components. So now go to the last slide. So I'd like to summarize my presentation. So the first, if we talk about reaction of dimethyl ester synthesis from CO2, we say that one of the main challenge of the reaction, of course, is catalyst, but also thermodynamic limitation. Because if we want to make dimethyl ester, we usually need high temperature. We also try to use high pressure. We can also try to lower the temperature by kinetics in this case. And we need to use bifunctional catalyst with some acidity, sites for methanol synthesis, and also phase for degradation. So conversion depends on copper dispersion. And if we want to reduce reverse water gas shift reaction, production of CO, we have to to increase the pressure, because high pressure basically favor formation of methanol and dimethyl ester and slow down reverse water gas shift reaction. The dimethyl ester selectivity is not much affected by amount of bronze site in the catalyst, and what is important also, observation that's confirmed by thermodynamics, that it's a steady state condition. It's impossible to obtain 100% dimethyl ester from CO2. You always have some methanol. And the last, which we can see here, the last phrase was that the interaction between two components in the functional catalyst should be taken into consideration, because it's important for, can affect to some extent catalytic performance. So now we'd like to also emphasize the contribution of team, because we have catalyst development, so it's actually our team was involved. Crystal, so Jean-Yves was involved in modeling, and Soraya was involved in process design and demonstrations. So there is kind of, the process, we have a lot of discussion between different partners about the catalyst, about this process. So I'd like to emphasize the contribution of my partners. And also I'd like to thank the people from our laboratory who contributed to this work, the postdoc Sarah, who was working experimentally, and we have Mirella, she's here, Robert, and Joel, who contributed to different aspects of say, experiments, characterization, and discussion, of course. And also I would like to thank all members of our team and permanent team and PhD students and postdocs. And I would like to thank you for your attention.
Time for a couple of questions.
I have a simple question. What is the amount of time that you spent into the work that you just presented? Are we talking a year here, or has this been 5 years of work that you just now presented?
No, it's for this, of course, I mean, it's our, this is also based on our previous background, but in terms of the project, now we say approaching to the end of the project, we actually started this work 3 years ago. So, and in terms of course, where I say, actually, the most intensive work was at the beginning of the project, because we have some deliverables to provide, but so it was we're now approaching the final of the project, so it's more focused on demonstration, not on catalyst design. So the most intensive work was at the beginning of the project. Yes?
So you show that methanol and the first water gas shift, that's direct competition when you want to make it full. Like if you increase the pressure, temperature, so it would make sense to split these two parts. So we first do CO2 or CO to methanol, and then convert methanol directly to DME. That make more sense?
Yeah, actually, there are two possible strategies. So, because in fact, when we talk in general, already in industrial process, because dimethyl ester is being produced, there are two possible strategies. One is so it's called direct process, which I'm presenting here. And there is indirect process. So each process has advantages. So of course, are you talking about direct process because it's one-step process, and you can produce DME directly from CO2. So it has several advantages. But I say two possible ways are possible to make methanol. So, but in fact, generally, if you compare two ways, so direct process are usually more advantages than indirect process. Of course, you need to optimize both process for methanol synthesis and for DME, so it's more challenging. So, but you will see, especially I think for this process, the big advantage will come from SEDMES. So we see because it's Soraya will present the result.
Can you please tell us if you have an idea which kind of maturity does this catalyst have in terms of industrialization, and if you have an idea in general in terms of how much they cost of this kind of catalysts, more or less. And
I mean, in terms of copper zinc catalyst, I think it's pretty high maturity. Pretty high maturity in this catalyst. Copper zinc, especially say for methanol synthesis, it's I mean it's have pretty high level. There are level for maturity. So dimethyl is a little bit different because we here, from our point of view, if you want to make dimethyl more advantages is SEDMES technology because we here will be doing in steady state conditions, and I would say. If you do steady state conditions, so the challenge is here that so it's say you always have methanol. So if you want to produce pure dimethyl acid, it's very challenging. So you always have methanol, and also what is actually you always have production of CO, but CO you can recycle. So it's not a problem with recycle. But in terms of catalysts for methanol synthesis, that's why we tried different catalysts for methanol synthesis, and finally we found that copper zinc based catalyst can be. I mean, you can also add some support or some binders. People say it can be alumina or zirconia based, and this pretty good, pretty satisfactory results for methanol synthesis. For dimethyl acid, we provide some. I mean, acid component, as I said, typically sub 34 can be, I mean, it's most commonly used. I mean, it's more give more because SEM5 to some extent is more challenging because SEM5 has strong acidity, and if you there's some problem with temperature control, it can result in some coating because it gives a lot of hydrocarbons and some coating. So sub is maybe. Also try to test here. It's embryonic. This is more like say. Research. Yeah.
I think we have time for one more question. I'll give it from the people joining us online.
Yeah.
So you conclude that there's always a byproduct of methanol in the reaction. Is this conclusion specific to this catalyst process, or is it a generic conclusion?
No. It's I think it's more specific to the steady state process because, in fact, you can. Because the goal of this process is to obtain selectivity to dimethyl as high as possible. And for example, you can, in steady state process, you are limited by thermodynamics. So because you have a continuous process, if you do in transient condition, you can increase what we already actually did. So I don't want to anticipate presentation. But in fact, if you're using SEDMES, if you remove water from the process, you enhance production of methanol because methanol from CO2 gives water. So you remove water, so it's shift thermodynamics to methanol. And also you increase dehydration of methanol to dimethyl acid. So in fact, if you want to increase, I mean, SEDMES in terms of has some advantages compared to the steady state that you can increase selectivity to dimethyl acid. So actually it's not, so higher production of methanol or byproduct of methanol is relevant to the operating condition. So, however, it can be can be suggested some solution how to improve.
That's all the time we have. Thank you very much.
Yeah, welcome.
Well, thank you for having me. I'm Jan-Willem Könemann from TNO. And I've been asked to give you a short introduction in the synthetic fuels and chemicals cluster that I lead at TNO. The technology that we develop, also supported by the E2C project, the SEDMES technology, is part of that cluster. So I will give you a highlight of what we do in the cluster, and as well I would like to tell a little bit about the potential of DME. Well, first of all, what do we do? In the synthetic fuels and chemicals cluster, we produce the fuels and chemicals industry and the transportation sector needs to defossilize, to get away from fossil feedstock and get into more sustainable fuels and chemicals. And there are, well, basically two options there. You can have a bio fuel or feedstock, or you can have a synthetic fuel or feedstock. Now, my cluster is all about the synthetic part. And as an expert in CO2 capture, and also with a lot of expertise in electrolysis to produce hydrogen, my cluster combines the captured CO2 and the green hydrogen into new hydrocarbons. And what we would like to do is to have a simple, effective, robust technology that in one step, with high conversion rates and with high efficiency, produces an array of chemicals. So we're talking about in one step producing the ideal syngas for Fischer-Tropsch synthesis, which is used to produce, for example, kerosene, diesel, or naphtha. Formic acid, methanol, of course DME, the topic of today, and olefins like ethylene, propylene, which is also a route to jet fuel kerosene. When we look at the synthetic market of the future and the commodity chemicals of today, is what we see, the costs are dominated completely by the cost of green hydrogen. And therefore, we get a total different picture in the future, because a very cheap commodity like natural gas, if we have to produce that from CO2 and green hydrogen, we need a lot of hydrogen and also a lot of electricity. So other chemicals may become much more important in the future than they are today, because they require less energy and therefore they are more attractive and cheaper. Now, with one molecule of hydrogen from CO2, we can make formic acid, a very small commodity at the time, or carbon monoxide, syngas, which is a large intermediate in the industry, which two hydrogen molecules we can use formaldehyde with 3 methanol, and when we dehydrate, we go to DME and ethylene. And as an example, well, take formaldehyde. We would like to produce formaldehyde from CO2 using only 2 hydrogen molecules. Currently, formaldehyde is mostly produced from methanol. So you have methane, you reform that into syngas, the syngas into methanol, and you oxidize the methanol to formaldehyde. But it is, of course, not very efficient if you do this synthetically, that you first try to make either methane or methanol and then burn that hydrogen off again to produce formaldehyde. We would like to do that directly. And those technologies are all developed within Dieulot and in many other organizations around the world. And also, I currently, within the cluster, we have 3 projects producing kerosene. 2 of them are looking in the most robust and ideal way, reverse water gas shift to produce syngas as the ideal feedstock for Fischer-Tropsch synthesis to make kerosene. With the ideal feedstock, I mean that it's not only syngas, but it's the right composition of syngas, the right temperature, the right pressure, so that you can directly connect from one reactor into the Fischer-Tropsch reactor. But we are also working on a much more efficient system, which is coming from CO2 via methanol DME to olefins and then to kerosene. And why is that much more efficient? because we do not have side products that we only produce kerosene. So all the hydrogen, all this costly hydrogen will be in the kerosene, and there will not be LPG side product or a heavy side product. Now, the technologies we develop are either process intensification technologies. We would like to have one reactor with high conversion in one reactor, eliminate large recycles, and reduce energy consumption. We would like to have a high selectivity for the desired product, so only produce what we want. When you have two pure incoming feedstocks, CO2 and hydrogen, you would like to have a pure product made, and of course enhance the efficiency. And in the process integration technologies, we, for example, integrate CO2 capture with utilization. So that means that we capture CO2 in an amine, for example, and then do the hydrogenation reactions in the capture liquids instead of first producing CO2 and then combining hydrogen and CO2 in a separate reactor. Well, when we talk about DME, then we have two very relevant technologies. One of them is a topic today, which is the SEDMES technology you see on the left. Now, I'm not talking about SEDMES because my colleagues will tell you a lot more about the SEDMES technology. But we are very proud to have such a nice containerized pilot system built, well, which you will see later this day. SEDMES is currently at TRL 5, and with this containerized unit, we already have the projects to push it forward to TRL 6 by bringing these containers in a more relevant environment for testing. In competition with SEDMES internally, I say competition, but there is enough room in the energy transition for a lot of different technologies and a lot of different projects. We have the Sienna technology, which is actually doing the same. In situ, separating water from the reaction. Now, I will not go into the technical details, but where SEDMES uses adsorbents with the catalyst to take out water, Sienna uses a membrane system, and inside the membrane system, the water is condensed. So with Sienna, water leaves the reactor, the catalytic reactor, as a liquid, making sure that all the hydrogen remains in the catalyst where it is used to produce the desired product. Now, both technologies at this moment well, produce DME, but we're also having projects for both technologies to look at syngas, so produce CO and hydrogen mixtures, as well as olefins like ethylene. Now about DME. DME is not a very well-known chemical industry. It's not as large as for example, methanol. I always explain that DME is a very friendly chemical. And how better can we explain that by saying that DME is typically the propellant which is in your hairspray. So you spray it well on your hair, so it has to be safe and friendly for yourself. So it's a modest bulk chemical. There's a considerable production in the Netherlands of DME, which is mostly used for hairspray indeed, but there's also DME production a lot in China. But when we can of course produce this DME, but DME is also perhaps an ideal replacement for diesel, because in a diesel engine, DME can combust and can completely replace diesel, or you can even mix it with diesel in the engine. So the engine itself does not have to be changed. Of course, you need a different fuel tank, you need a different fuel injection system and control system for your truck, but you can have this dual fuel. You can run a truck on both diesel as well as on DME, or when you go steep uphill and running on DME, you can add diesel with your DME in the truck. So it is an ideal fuel also for electricity generator sets, for example, where you are off-grid in a construction site, for example. The challenge, I think, is the infrastructure. There is no large infrastructure like we have in gas stations at this moment on DME distribution. So that would be a challenge in adopting that in the heavy transport sector. On the other side, we have the current LPG market. Well, within LPG, DME is the ideal replacement. LPG is of course used for off-grid heating and off-grid energy like you have in farms, or well, it is not so widely used in the Netherlands, because in the Netherlands we have a very dense natural gas network. But in Europe there's a lot of well, remote locations where you see these, for example, this Prima gas tank in the yard. Producing propane or butane synthetically is not very efficient. Producing DME is really a lot more efficient. And the great benefit of DME here is that it can use exactly the same infrastructure. It is contained in approximately the same pressures. So you have, you can use the same tanks, the same filling stations, everything is already there. You can also mix it with propane, butane. So this is a potentially huge market on DME. And two of the largest companies in the world, one of them Dutch, one of them Chinese, this year have created a joint venture where they invested $1 billion to produce DME on a large scale. So a lot is happening right there. And last but not least, like I already explained, DME and methanol are an intermediate for us in the novel route to synthetic aviation fuel, which is something which is at this moment becoming really huge. So there will be a lot of processes in industry which will have DME somewhere in the process on their way to aviation. Now, when we look at the challenges that we face, well, first of all, our technology. We have to make sure that our technology is ready to be implemented on the market. So we need to reach this TRL 6 or 7 so that we can transfer this to industry. Now, for SEDMES, we are nearly there. We have the unit built. We are going to test it in industry. So perhaps 2 or 3 years, we will be ready for our first large demonstration or small commercial facility. With Sienna technology, we will have, we are currently in TRL 3-4, so we'll have some years to go. We have to show robust and reliable operation in this relevant environment, of course, and make sure that there's enough trust for the commercial parties to actually produce that. And one of the things we have to do is that currently producing DME synthetically with the current high electricity prices is a lot more expensive than the DME which is produced from fossil resources. And when you look at the columns on the right, you see that the capex from the electrolyzer and the electricity consumption is the dominant factor. In fact, you could say if the electricity was cheap, really cheap, then we would be cost competitive compared to fossil DME. And that is also something we will, of course, we can wait. We can wait 10 years and wait until there's enough renewable electricity that we can use. We can also wait until the electrolyzers have become much cheaper. But we can also anticipate at this moment. I think 1 or 2 weeks ago in the Netherlands, we had our first day that as a consumer with a flexible electricity contract, you could actually get a little bit of money by consuming electricity instead of paying for the electricity, because it was sunny, the wind was blowing, and there was a slightly negative electricity price. Now we can also, of course, we don't count on negative electricity prices all the time, but we can use that for the production, because if there's a wind park at sea and that electricity cannot be put onto the grid, you can produce hydrogen, but also hydrogen is not very easy to store. So if you can produce DME at that moment, which is easy to store, for which there is a large market like in the LPG, and that DME in that case can use low prices or perhaps very low prices for electricity, you are cost competitive. But then you have to operate on dynamic loads. You have to be ready to operate only in the hours that the electricity prices are very profitable. And that is something that we would like to investigate, the dynamic load operation, and also how will this work into a business case, because it also means that your installation will not run continuously, so you have less production hours. So these are the challenges that we will have, and especially with the SEDMES technology, we're looking forward to realize the first commercial facilities together with market parties in the coming years. Thank you.
You're talking about high price of hydrogen,
yeah,
the whole process. What about the CO2? Where is that coming from, and what is that price related to the hydrogen?
In this example, we did use a cost for CO2. I think for CO2, one of the most important things is you would like to have sustainable CO2. So you would like to have CO2 which comes from a, for example, from biomass residues, for example, or direct air capture, for example, so that your DME is completely sustainable and green, like your hydrogen. And then at this moment, there may be a serious cost with that, because direct air capture is expensive, also costs a lot of energy, and there is just not enough CO2. So we now have a CO2 problem, but maybe 10 years from now, we will have a carbon shortage in industry, and how to deal with that. At the same time, we are in an energy transition. So I would say any CO2 that we capture at this moment and reuse to do something good with it or use it again will be positive. But of course, knowing that in the end, it all must become completely sustainable. So if we stop with fossil fuels, waste incineration after recycling will become green CO2 as well. So it's very hard to predict the prices of CO2, but within this analysis, we have used a cost for CO2. So we did not count on a benefit, so avoided taxes or something like that.
So I guess some the issue for electrolyzers to small amounts doesn't even work if you can use it step to produce carbon monoxide.
I did not completely.
Because our focus is really about CO2 electrolysis to carbon monoxide and oxygen. So do you consider this possible route that you produce first carbon monoxide? It's probably much more efficient as a products.
You mean that okay? You mean that commodity fuels and chemicals, there will be more fuels and chemicals containing oxygen in the future than right now. Is that what you were saying?
Yeah, so you take CO2 and you produce carbon monoxide by electrolysis.
Oh, that use that oxygen.
Yeah.
Yeah, well, that is.
Use this carbon monoxide for chemicals. So does it give any value in the presence of the reactors which that is an intermediate step for carbon monoxide synthesis?
Yeah, so I'm not sure I completely understand you. I'm sorry, but perhaps you can talk.
The direct conversion of CO2 to products. We are doing this, and the direct electrolysis of CO2 carbon monoxide. So we are doing this, and we are doing it in the same project. So within the project, we have compared the two routes of valorizing CO2, both directly as indirectly. So we call the DME production the indirect valorization of CO2. We can share with you, let's say, an economic evaluation, preliminary economic evaluation.
Because it's interesting because you take kind of water, less water, but actually you can take the oxygen earlier to step CO2. That's why we should have one session. It's interesting.
What we didn't do was not to introduce the CO from the direct electrolysis to this process. So we did do a comparison of completely going only direct electrolysis or going CO2 renewable hydrogen to DME. It's an interesting thought to go further.
Yeah, so now I understand, but at TNO, I think there are maybe 6 or 7 different technology routes developed that produce CO or syngas. And both well, direct with electrolyzers in different ways or reverse water gas shift in different ways, plasma, molten metal. There are all kinds of ways to use syngas, and we'll have to find out. I think in the end there will be a mix of technologies on the market, which will have specific benefits for specific cases, but also probably we are developing some technologies which will not be successful in the end. That's part of research.
I think we need to move on. Thank you very much.
Yeah.
Okay, so hello everyone, my name is Soraya Sluijter. I'm also working at TNO. I'm the project manager of the Power to DME line in the E2C project. And I had some nice speakers in front of me who already introduced DME and also I think the technology a bit, but I will go into a bit more detail at least. Well, I'm very happy that you all came to Petten today. It's a nice day. Me and my colleagues are based here on the coast, and we are committed to a more sustainable process industry. So we would like to go to CO2 neutral process industry. We're working on several technologies to realize that. And the two most important, I think, for in this project are the CO2 capture and utilization and also the electrification of the industry. And those are combined in the E2C project. I think you've already seen some of these reactions before. Like Jan-Willem said, we are focusing a lot on process intensification. So we want to combine conversion step and, for example, separation step in one to optimize and intensify the process. And we're looking into different types of reactions. For carbon capture, we've developed the sorption-enhanced water gas shift reaction to capture CO2. At high temperatures and high pressures. And we're also looking into CO2 utilization, in which we capture the water that's being formed in different ways, using sorbents or using membranes, for example. And today I will focus on the last technology, sorption-enhanced DME synthesis reaction. Like Andrei already very nicely introduced, when we want to produce DME from CO2 and hydrogen, we also produce water. And this reaction is limited by the thermodynamic equilibrium. If we now can remove the water, we can shift this equilibrium to the side of DME and produce DME in a higher yield. That's what we're trying to do. We can also do that for other products. You can see on the right side for you. You can see here, if you have a low steam partial pressure, we can get to very high, oh, where am I? Mole fractions of DME. And the same is true, for example, for methanol, which is over here. If we go to higher steam partial pressures, the mole fraction of the product of your desired product drops significantly. In our group, we are always trying to develop process both experimentally and also by using modeling tools. So I will try and show you a little bit of both what we've done. Within the E2C project, the idea is that we start with renewable electricity, of course, water with electrolysis. By water electrolysis form green hydrogen, combining that with CO2 to produce DME. And we are developing a pilot for that in the E2C project. So in a bit more detail, the different steps that Andrei already showed you as well. First, the step to form methanol from CO2 and hydrogen. And then the methanol has to be dehydrated by a different catalyst, as Andrei has showed you. And in this sense, you can get to yields that are shown over here. Also, to get back to the question in the back, we can also use CO or syngas as a feed. But if we use CO2 or a mixture of CO2 and CO in this way, you can only reach a limited yield of DME. And we want to increase that. So we do that by removing the water that's being formed in the different steps and adding a sorbent to do so. See, there it is. It's under that, but we add another material that can absorb the water. So in our reactor, we have 3 different materials. And combined, they give us the possibility to really increase the selectivity towards DME. DME is the green bar. And in this way, using this technology, it doesn't matter if we use CO as a feedstock or CO2 as a feedstock. So we can use both. And we see it as an advantage that we can actually use CO2 directly instead of first doing electrolysis step to use CO. Well, Jan-Willem has introduced DME while we were working on this chemical. We see a lot of potential for DME in the circular carbon economy. So I won't go into detail on this slide. So a bit about the technology development. We started out very small in the lab around 2014, starting with 25 grams of materials in the Flex project, which was a European project. And we have, over the years, scaled that up to building the actual dedicated pilot that we are building now. It was very convenient that we already had the infrastructure for the other Sorption-Enhanced technology that we're developing. And that really helped accelerating the technology development for SEDMES technology. You cannot see the targets of the new pilot, but the targets are 3 kilograms an hour of the DME production. And another condition was that it has to be transportable. So that's why we made it containerized. It's still quite big, so it's not like very easy to transport, but it is possible. And with that, we can also test it on industrial sites or different locations. This pilot was designed and engineered in-house at TNO, has been built. You can see here different columns. As we have a process that uses sorbent, if you want to do continuous production, we have to have different columns, because at one point your sorbent will be saturated and you will need to switch to the other column to produce continuously. So at least we want to have 2 columns, but if we have more columns, we can play around with the process a bit more and optimize it further. So this time we came to a 3-column system. We have some room for the 4th column, but we didn't have budget for that. So we left it at 3. So we have 3 containers. One is the most important, the heart of the pilot is the reactor container, which is standing over here. And the others is for the analysis, analysis and flare and infrastructure. There's also an electrolyzer already, electrolyzer already standing next to it. But in this project, we will not do the actual coupling, but we will do so in the next project. But we are investigating the process for the techno-economic analysis for all the desk work we did. We are considering really the power to DME process. So the end of last year, the pilot, at least the reactor part, came to Batten, and I have a movie for you to show how that was put into place, and also with some more explanation around it. At this moment, we're finalizing the last bits of the construction and doing the commissioning of this pilot. So I'm very excited to show you all this afternoon. I hope that this will work. There's no sound. Is that right, Jan? Can I do something with this? Yeah. No, now it's actually turned on. Well, it has some subtitles which you can just about read, I think, or not, but at least here you can see 2 cranes and the reactor tower coming in. It's being put into place. I think the link is also in the presentation, and Aaron will show it. We'll send it around, so then you can, if you want, you can have another look at it. I hope that online they are able to hear it, but I'm afraid not. Actually, explaining what I just explained about the process, I hope it was already clear. This is Johan, our colleague, who will be the operator of the pilot. He's also explaining what you can do with DME, and you already know now. So. This is another part we did also in E2C. We also looked at the electrolysis side. Xiaohong will tell you a lot about that later. We also actually developed a testing station for AEM electrolysis, and this afternoon we'll also show you that. I won't tell you anything about it in this presentation, but that's also part of the E2C project, and we will show you this afternoon. So this is it, but you will see it this afternoon in real life. So yeah, then we are still having some challenges in the scale up. I think Jan also mentioned a few more market related challenges, but we also have some technical challenges. We see a trade-off between the productivity that we get versus the selectivity of our carbon product, and so the selectivity towards DME. And with the modeling, we try to solve that by optimizing the cycle design. Another thing that we are still looking into, we don't have to recycle our CO2 or methanol, but CO is something that we could recycle. Also, we have several steps in our cycle. One is the reaction and the adsorption. That is the step in which you produce DME, your product. Then we have a blowdown step and also purge step. At this point, we're using hydrogen for that. But like Jan-Willem said, hydrogen is very valuable and very expensive. So we would like to perhaps recycle that stream. And then you have a repressurization step. So these are the different simplest cycle looks like it's this: adsorption, blowdown, purge, and repressurization. Like Jan-Willem also mentioned already, we're also looking into looking at different use cases and proving those experimentally. So looking at different sources of CO2. Well, hydrogen is can also vary from different water electrolysis sources, for example. So, but we're mainly looking now at the CO2 side. So what industrial gases to use as a feed for our technology. And then of course, on the other side, you also need to read some specific specs if you want to use DME as a fuel or as a building block for chemistry. So that those type of things we're looking at. So yeah, like I said, we see a trade-off in carbon selectivity and productivity, and that's shown in these two figures both actually. Here on the left graph, the red, where am I? The red squares are the productivity, and the green bars are the DME yield again. So you see a clear trade-off, and we want to be somewhere in the middle. This is depending on, for example, the space velocity that we use. But there are more things to play around with, and also the different cycle design. So what step, how long you will use your column in one step, when you will switch your columns to produce the highest amount of pure DME. So we did quite a lot of modeling work. I'm not an expert in this, but I will try to explain. So why we use this modeling and simulation tool for is to optimize our process, to synchronize the certain number of columns that we have. So I already told you in this pilot we have 3, but maybe in the full scale we may have more columns to work with, and optimize the process parameters such as pressure, the temperature that Andrei mentioned, the gas velocities, and so on. And of course, all these models are always validated then later in our smaller scale equipment, or now in the pilot that we have. So for the pilot, we use the following boundary conditions: 3 reactors, and actually all the reactors, I forgot to mention, have a shell and tube reactor design to optimize the heat management in the reaction and the process. And each reactor has 19 tubes, and oil will be surrounding each tube. Of course, we're taking into account the flows and the pressures that can be used. And the maximum pressure here was 20 bars. And actually, I have 2 examples what we got out of the cycle design. So it's a similar design. So one column will be in absorption mode, then another one is in purge mode. And as you can see, the absorption is a bit shorter than the regeneration part. You need more time for that. So that's why it's also important to have more than 2 columns. So this is the cycle design, and my colleague played around with the timings to get to an optimum productivity and selectivity. And with this cycle design, we got to 76, let's say 76% of DME in one step, and almost 2 kilograms of DME per hour. But she also looked into going to higher pressures, for example. So a similar cycle design, same temperature, same setup, everything, but then go to 50 bar. And then we can see that we can actually reach the 3 kilograms an hour of DME, and also have a very attractive DME sensitivity of 95%. So that's just an example of what we do with that. I would also like to show you some experimental results. Of course, we don't have any results with the pilot yet, but some previous results. So in the previous project, the Flex project, we showed that we can regenerate with only pressure swing regeneration. So in before we also always use the temperature swing, but that costs a lot of time. So here we found out that we can only do pressure swing regeneration, which also very much helps the productivity. And we've proven the process for 300 hours of continuous operation, more than 130 cycles. And here you can see, the productivity and the selectivity towards DME. We've also shown that we can use both CO2 and CO as a feed in the ratio, and this doesn't affect productivity or the sensitivity towards DME, as long as we put stoichiometric amounts of hydrogen. And we've also seen that we don't need a very pure CO2. We can actually use a stream that has a lot of inert gases. Of course, some gases or impurities may have an effect on the catalyst, but we can use up to 30% of inert gases without any influence on the process, which means that we don't have to have this very expensive CO2 capture step in between. So for the upcoming experiments, what do we want to do? So one of the first things is actually coupling the water electrolyzer to the SEDMES technology also experimentally. So that we will do in the Kansen for West project, in the field lab for industrial electrification in Rotterdam. But first we can do some testing in Patton, luckily. And there we will look at the different CO2 streams. Different industrial residual gases, also looking into this inert gases. So we have one case from Tata Steel, so for steel production, and we will also, so before we've also looked into biomass gasification as a feed source. And then we hope that after that we can scale up the technology further in another project that we are developing at the moment. I have one slide, I think, about the business case. Jan-Willem already showed you this graph here on the left. So we found indeed, assuming a cost price for CO2, and a lot of assumption actually, which you can find in the paper if you're interested, that production costs are now around 1.3 kilograms per DME for 23 kilotons per year plant, which is way higher than the market price, which you see over here. And we can also see that the main cost is coming from the green hydrogen. So the good news is that SEDMES is using the hydrogen quite efficiently. And we also are a partner in the project. The University of Sheffield also did, not really an LCA, but studied the CO2 footprint. And if you compare it to diesel, and then they could see that we have 80% reduction compared to diesel. We also did the sensitivity on, for example, CO2 price, I think. Yes, that's here, but we didn't make it negative. And what that does to the price, but all remained above the current market price still. So we have some way to go. That brings me to the end of my presentation. So the most important output of the E2C project is the pilot. It's one of the pilot demonstrators. The other one will be presented in the next workshop, which you will visit this afternoon. It's almost operational. We're working on scaling up and optimizing the process further and trying to optimize the trade-off between the DME selectivity and the production rate. We are also continuing on looking at the downstream processing. We will do so in the field lab for industrial electrification. And we're looking into different use cases at the moment. So with that, I think that's it. Thank you for your attention. We did not do so yet, but yeah, that would be interesting. I think we also didn't really look into that with a study yet, but of course that would be perfect, and we can also recycle, reuse the water again.
Yeah, when you have a pressure swing, you have a water mixed with some amount of CO2 or hydrogen. You need first to separate it from this waste.
Yeah, I don't know exactly how pure indeed the water is that will come out, so we might need some separations before, but we have to look into that if that would be viable to do so or not, both experimentally and also cost-wise. But that would be interesting indeed. Thank you.
Thank you for a very nice presentation. What catalyst do you actually use in Thailand?
Yes, so we use commercial catalysts. So Andrei has done some very nice work in developing some catalysts. So we are still looking into improving those, but we are using commercially available catalysts. So also copper, zinc catalysts, and then alumina. Yeah.
So I have a question from online.
Yeah.
Is that estimated price of 1.3 euros per kilogram based on a fully optimized and scaled up process with mature manufacturing of components, or is there scope for that price to reduce further in the future?
Yeah, I think there is some, of course, every step we make, we will do a reassessment of the techno-economics. So this is based on the cycle design, for example, that we have now, but we did scale it up to 23 kilotons a year planned. So we did, yeah, some cost optimization in that, but that's also assumed, of course. But the technology is as it is now. And actually that scale was determined by the size of the electrolyzer. That's now commercially available. Yeah.
Which kind of utility you are using to build out the reactor? And do you need this utility to build out the reactor also with the incineration and the absorption?
No, we will use one temperature, and we have that's why we have the oil in between the reactors. So there is an oil, and that will be pumped around, but that will be reused the entire time. So we don't need active cooling in that sense. So that's why we have this design.
So the technology for sorption-enhanced synthesis mechanically has been applied to other products as well. And if so, have you looked into the processes to see what lessons learned were there that you could apply this?
So we are developing actually one of those. That's the sorption-enhanced water gas shift reaction, in which we use that for CO2 capture and production of hydrogen at the same time. And that helped us a lot. The lessons learned there, the facilities that we have developed for that technology also, but also the knowledge that we've gained. Of course, we've also been, we usually work in consortia with other partners, and we're also learning from them. But yeah, I would say we've learned the most of the development of this other technology that's already a bit ahead of the SEDMES technology. Yeah.
Question about safety, maybe. How's the reaction control? It's always very easy to control temperatures and pressures. Was there also already chances for runaways?
I think that's a very good bridge to the next presentation, actually, which comes after the break, because that's something that the University of Lille has looked into, controlling the process.
Good. So we have two more presentations, shifting gears a little bit from the DME part to the hydrogen part and some of the control. So we have one presentation from the University of Lille, and that will be followed by a presentation from the University of Exeter. And after that will be lunch, but we'll discuss the rest of the logistics then. So the floor to
Thank you. Thank you. Again, good morning. Yes, then this presentation will be given in two parts. First part will more concern diagnosis and supervision. Second part will concern more control of DME. Maybe just two words. This is just my group, Professor Bouamama. This is our group, which belongs to Crystal Laboratory within CNRS. And we are more working on diagnosis, supervision, and control. Maybe just two words. There are some presentation. We see that in order to improve any technology, we have always three possibilities. The first possibility is the hard level, means to improve the material point of view, the equipment. Second level is process, what we already presented. And the third level is system point of view or information level. This is more concern communication and information technology, who belongs to this part. But anyway, we have of course to understand exactly what is the process, what are the main phenomena in the process in order to have the model for diagnosis and control. Okay, maybe just two words about this presentation we give concern production of green hydrogen and of course control of DME process. Main results are provided from a PhD thesis given by Sluijter, like I think today Jean-Yves is as well. He was one of the referee of this PhD thesis. And we have a laboratory platform where it's possible to have some experience. This laboratory platform is in fact a multi-source platform for production of green hydrogen. Because as you see here, it consists of renewable energy sources, solar and wind, electrolyzer, okay, to produce the hydrogen. And of course, we have the fuel cell in order just to see how the hydrogen can be used as a vector of energy to produce energy. And of course, in the second part concern more power to gas and power to industry. This part is not in our lab. This is why we are working with Dieulot and with Andrei to more for control this part of the system. As you see, it's not easy, in fact. Why this is why there is some issue concerning production of green hydrogen, because as we know, sometimes there is no wind, sometimes there is no sun. And how to manage first this intermittence of renewable energy sources. This is why we have several technological and scientific issues. The first, why? Because mainly of this intermittence aspect of sources. Then the question is how to ensure the availability of energy. This is very, very important from societal point of view. It's easy to do. We are going to produce green hydrogen, but we'd like to live well and to have always the energy. Then first, how to ensure this availability of energy, regardless, of course, of the state of the sources. And what is important, we know that, as speaking about, of course, the price, we know that the durability of electrolyzer or fuel cells is really a problem because it's very expensive. That, for example, fuel cell is about 7,000 euro comparing with little part. It's very expensive. This is why the durability of this equipment is very important. And how to improve, of course, this durability, but also safety. It's hydrogen, then we have to ensure the safety and security of personnel. And of course, what's important is how to reduce the maintenance cost. This is why we need this online supervision system design. I'd like to give some talk about supervision because from industrial point of view, sometimes supervision is monitoring. No, supervision is not just monitoring. Then, of course, if you have just this part, this is just monitoring. This we have process, we have, of course, sensors, controllers, and actuators, and we have some graphical user interface or just from which it's possible to control the system. But what's happening when we have fault in the which can occur in the process sensor or controller or maybe actuator? We have to design fault detection and isolation level for online fault detection and isolation in order to inform, of course, the supervision platform. And what is important, the question is how we have to stop or not the process when there is a fault. It's a very important question because usually in the industry, we have just the thresholding system for any parameters, what we want to know, what to do after if there is a fault. And not only is it really a fault, then this fault tolerance control level, it means we continue to control the system even in faulty mode. And actually in the industry, there is new, very difficult. This is why in this part, we need, of course, the hard level and the process level. There is a fault, it's okay, but what is the lifetime, that is the remaining useful life. It's very complicated because in fact, it's not easy to have a degradation model of any equipment. Then this is why when we have beginning of degradation, we have not to stop to say if we are in the flight, if there is any fault. The question is, we can reach New York or not. It depends, of course, of the remaining useful life of this person. Then to estimate this remaining useful life, it's another topic very important from industrial and from fundamental point of view also. Okay, then our approach is as follows. The first step, in fact, which is also important from industrial point of view, is the design of the system before real industrial construction of the process. This part is done offline, based from the failure mode effect and critical analysis model, but model at this step, we don't need any numerical value of parameters, and we can know at this step where we have to place the sensor in order to satisfy some technical specifications. Sensors are sometimes very expensive. Sometimes we don't know where to place it in order to satisfy some technical specification from control and from diagnosis point of view. Then after this step, we there is a fault. I will have to isolate the fault. What's happening? I am in degraded mode. I switch off maybe. Up. Yeah, this is nice example of fault detection and isolation. Yeah, then the second step is from sensors we have data, we can have monitoring, and we see just value of different parameters. But the next one is to design the fault detection and isolation algorithm in order to send a list of faulty components and, of course, operate decision. We can use equations, but we can use deep learning classification or database diagnosis in order to generate those alarms, but also to have, from prognosis point of view, remaining useful life, and if necessary, to have a recovery decision. Our application, of course, concerns all the process, but I am just speaking about the electrolyzer. In the electrolyzer, we have first, of course, we need the model is a very complicated system. Why it's complex? Because in fact, what is very important, if we have mechanical system, we have just torque and speed or force and linear velocity. But in electrolyzer, we have three energies, coupled energies. It's very complicated. We have electrochemical energies, we have mechanical energies, electrical energies, and of course, fluidities, pressure and flow. Then those coupled energies, we have to modelize them. This is what we have done during this periodicity. This is interesting paper in generic approach to have this dynamic model. Again, I speak about chemicals. You always have stationary model, but sometimes we can have pressure very high. Then to design the system, it's important to have the dynamic model, is to take into account the time. Then having this model in a generic and in modular fashion system, taking into account several phenomena, we have to design the diagnosis algorithm. The system is working in normal situation, of course, when the equation coming from conservative law equations is equal to 0. But of course, to evaluate this equation, we need parameter values of each parameter. This is just very simple system. Then when everything is healthy, then we have this residual closer to zero, but never equal to zero. This is another problem. Because if we have false alarm, we have to stop the system. Or we have false or police alarm. Why? Because in fact there are two very complicated issues is uncertainties. Uncertainties first from sensors, and of course uncertainties from parameters. What we develop is to take into account those parameter uncertainties in order to have a robust decision to the operator, in order to be sure that it's a fault or it's not fault. Why? Because in fact, this is what we show here. This is, we take into account those parameter uncertainties in order to have accurate decision. But in fact, in the electrolyzer, it's not low home, it's not just very simple resistance. This is application to obic resistance, or it could be to, for example, thermal resistance in the electrolyzer. The equation is very complicated. This is why this equation can be evaluated in order to know if there is a fault or not, taking into account those parameter uncertainties. Second step, very complicated too. Okay, we have alarm, but we don't know exactly where is the origin of this alarm. Then we have to develop some decision-making tool in order to take into account. Then this is a matrix, named fault signature matrix. In this matrix, we have column and rows, of course. Then in column, we have some fault indicators. Fault indicators are not sensors output, are combination of sensor outputs. Then there are some residuals, and in rows, we have fault we would like to detect and to isolate. This Boolean matrix, you see that there is 1 and 0. There is 1 if this fault is sensitive to this residual. Means the fault FG is sensitive to residual L. Else it's 0. Then any fault have some Boolean vector. This vector, if it's not equal to 0, then I am sure that I can detect the fault. If this vector is different from any vector, then I am sure that then I can isolate the fault. This is the idea of the reasoning in order to detect and to isolate the fault. This is just from mathematical point of view how we can develop this algorithm. This is now just our application. In our application, of course, then we will have this graphic interface. This is all the algorithm. This is the supervision software. As you see, we can have the efficiency calculation, and we can also have the diagnosis and the prognosis of the system. The system consists of 2 solar panels, 1 turbine, 2 batteries, the PLC controller, electrolyzer, of course, and the storage of the hydrogen. Then, this is the graphical user interface. Okay. Then there are here, as you see, all several fault indicators. Then we have, of course, to reason concerning all those residuals in the electrolyzer, the 1 turbine, the battery, the solar panel. And we can introduce fault. Sometimes it's not easy because it's dangerous to introduce fault. In our case, we can introduce some blockage, for example, emulation of the blockage fault in our process. Then, as you see, several residuals are now different from 0, but we have to know, because all variables are coupled, we have, of course, to know exactly which kind of fault. Then when we stop the fault, of course, the residual will back to 0. This is the first conclusion concerning the diagnosis after my colleague Jean-Yves spoke about the control. Then within this project, a generic dynamic model for electrolyzer has been proposed. This dynamic model is suitable for performance simulation, sizing of cores, efficiency calculation, control, diagnosis, and prognosis. And it is linear fractional transformation based on bond graph theory and diagnosis. Has been proposed for PEM electrolyzer diagnosis. The supervision platform can be used by the partners, of course, at any time, because it's laboratory platform. Then you can introduce any fault. It's not very dangerous and it's not very expensive comparing with the industrial one. And of course, optimism will be provided to the in order to reduce the maintenance cost of the electrolyzer and to test feasibility and performance of the system for scaling up and sizing. This is why we have very nice contact with Coderite. Between us at the beginning, we thought that Coderite is a more commercial group but in fact, they are very interested for electrolyzers at high temperature. Second part, please, Jean-Yves. I think we can have a question after presentation. Okay, as a project, we provided a bibliographic study of how could, in fact, advanced control and optimization could help for a better process control and have improved results. So here we can see something is we, in fact, in real time, we have some monitorable inputs. That is here, for example, we talk about CO or CO2 mass flow, hydrogen mass flow. So in real time, what are, in fact, the best values and operating values to design to get the best of the process. And this is not really simple because, in fact, when we have a very simple control, of course, it's possible to do that, but the process is very, very complex. As we've seen before, as was presented before, high number of reactions and variables in a tubular reactor. And moreover, what happens is that there is an absorption stage. And of course, as in fact, adsorbent is loaded with water, there is some kind of moving front inside the tubular reactor. And all this was already modeled by TNO. But the problem, in fact, with this kind of model is that it's not really suitable for real-time control. Why? Because it's very complex model, and also because it takes a lot of time to compute. So here, the challenge is how can we alleviate that, and what are the challenges regarding this? In fact, what we try to do is to have a simplified model. So here is very simple set of ordinary differential equations. That means how it moves with time, in fact. So we can see here for example, in a solid, we have a model output, and also with the dotted points, there are the experimental points. But here it's very local models. We cannot really use that for when really we have a very important operating range. The problem also is to know what kind of sensors we could install. For example, we cannot really measure DME in real time, but we can measure CO with appropriate sensors. So in fact, here, the problem is to know which kind of sensor we could install and what kind of model we can do. In fact, we reached a conclusion at the end of further work. In fact, because have a very simple model is not really suited,
and a very complicated model is not also suited for real-time control or real-time dynamical prevision. What we suggested is to have a data-driven model, that is a data-driven digital twin that could in fact replicate the operation of the reactor with time. So for example, we could use what is called neural networks. Neural networks, it's a kind of machine learning. So what is it? Basically, we have neurons, that is, we have some inputs, and then we have kind of function, and the output is a function of the inputs. So this is the most basic model. And then there are all these neurons can be connected together. Then there is a training process. That is, we can, in fact, what we try to do is to match the real input-output set with the output of the neural network. So what will happen is that after this training process is done, we can then have a new set of inputs, and it will generate the corresponding output. Of course, what is really interesting is that today there are a number of networks that really work very well and can get some kind of impressive results and a real ability of, I would say, replicating from the existing sets of data. So what could be done, in fact, is offline. You generate with a physical model a very high number of data. It will take time, but the computers, they can do it and you don't have to do anything. And then after that, you can feed it to a model, and then this model will react with very little computational time. What is the purpose of doing this? The purpose, if I take the curve supplied by TNO, the thing is, the problem is first control. What is control? Control means that you want, for example, to stick some variable to a set point. That is, if I want to have 20 degrees in this room, then I can operate the heaters, and so that with time, then the temperature after some time reaches the desired set. When you have adsorption stage in DME production, then in fact you have no real set point, because when you reach the steady state, then in fact it means that in fact the adsorbent is fully loaded. So it's not really useful. So the problem is that traditional control in fact doesn't apply here. It's quite complicated and disturbing. So the real problem, in fact, is not really control. The first problem is to get some kind of optimal trajectory. What is the best trajectory to get? So here, in fact, we can define a criterion, and then we can, in fact, have an optimization problem over adsorption time, where, in fact, you can use a fast model just to get the best operating trajectory. And of course, this will be only offline. It supposes that the model is rather good, but this will be done offline. So you can get a trajectory, and then after that, the trajectory is some kind of number of points, and then maybe you can program it in a computer or electronic form. So all this work can be done offline. Then online, what you can do is, in fact, use either simple control algorithm, whether they work or not, or for example, because there are a number of control loops, imagine, in fact, having some other kinds of control that we may present after, but mainly, in fact, here you can have some kind of, for example, here predictive control. Predictive control means that you predict, in fact, the future trajectory at time t from the model. You can have a future, you design a future string of controls that in fact optimize your criterion. And then it's more easy, because if there is a very complex model, then in fact what you only need is to compute, in fact, to optimize your criterion using the model. Then there is a last thing, but that we did not really explore, was what Soraya said. It was also, in fact, that DME control is not only adsorption step, it's also cycle. And here we did not really explore that, but also cycle time can be a part of the problem and of the optimization problem. So our conclusion is that if we would like to use very advanced control, we can use data-driven, that is artificial intelligence techniques. And these models can be used for offline optimization, not online. So you can have the best trajectory, that is the best operating conditions over time. There are some control techniques that replicate the optimization criterion for real-time implementation. And of course, future issues, you have to consider the cycling behavior. So thanks for your attention. And so this is we didn't talk about fault sensitive control, but this is more coupled with what the Belkacem presented.
We have time for maybe 2 questions,
I see that you used the AI model, neural network and so on, in this consortium. Has there any work been done for the physical modeling? Modeling is based on the physical.
I didn't really catch your question. Il y a une approche à base du modèle physique.
So you tune the, you mentioned that you would tune your neural network model by physical model.
Yes.
Is there?
There is a physical model. Yes, this is what we did before. No, for yeah, for DME itself.
For DME, there is a physical model from Dieulot, and for our electrolyzers, there is a physical model also from ours. That is for electrolyzer. But of course, we need either a physical model or either experimental data. And this is the main issue that we have with artificial intelligence. We need data. If you have data, then it's simple. But the problem is that if the physical model is rather slow or very complicated, then it's not really easy to use it for real-time control.
I have also a question regarding the neural networks. So you train a neural network on conditions that you can measure and things that you can expect.
Yeah,
But
sure.
the problem with safety is that it's the things that you don't expect that go wrong. So what is how do you prevent your neural network getting false input that is nonsense, by providing a positive output where it's saying we're fine?
Yeah.
Is it easy to recognize something like that?
I have first general answer. There is actually very open research concerning digital twin. This is how to have the simulated model very closer to the real one. This is what we explain digital twin, but just modeling. This model can be in lumped parameters. This depends only on time, but also can be under partial differential equations. It means it depends on the space and the time. We can use it for training. I agree with you that actually everyone is speaking about artificial intelligence, but it's not easy to use it in the real process. This is why I'm giving that how to use it, but in some simulator, because and another issue is when you teach modeling for a student, you have parent testing, and then sample model is never usable. Sample model is not accurate, and complex model is not usable. Yeah, they are to resolve, of course, this difference.
I have also an answer for that. I mean, another project, but it's more on renewable energies for power systems. And we have this kind of problem, in fact. So we have two different problems at the same time. It's, I mean, we can estimate locally the model, right? And then the problem is then when we have a non-linear, we change from is to know whether, in fact, still it behaves well or not. It's a power converter, but does it behave? It's the same kind of problem. Does it behave well or not? And so there are two problems in one. The first problem is to have classification. So it means, do we know, in fact, the state of the process, whether it's faulty or not? So it's really a very big issue, because sometimes they can resemble one process is healthy and it behaves in some way, and another process is unhealthy and it behaves in another way, and sometimes it takes some time to make the difference between the two. Then after that, when you know that your problem is when your process is healthy, for example, just try to estimate the conditions and the problems. So it's two kind of problems, and then you need, of course, different kind of indicators. And it's not that simple. There is no
we have a really accurate model for use control. This is open question. We can have the next project in digital twin.
You always have to.
Thanks very much.
Thank you.
Good morning, everyone. I'm Xiaohong Li. I'm professor of energy storage, working in University of Exeter. Very pleased to be here to join you to inform, communicate with you our research on IEM water electrolyzer for hydrogen production. We are one of the partners in the E2C project. Hydrogen is so important and it's simply fascinating. Hydrogen, as we know, makes up 3/4 of the mass of the whole universe. currently, globally, hydrogen, there are more than 70 million metric tons of hydrogen produced. Traditionally, the big use of hydrogen is for ammonia production for fertilizer. And actually, 50% of hydrogen is for this use. And also hydrogen used for petroleum refinery and for metal and steel production. And now that we talk about hydrogen economy, it's use the electricity from renewable to produce hydrogen, and they use hydrogen for fuel cell and for other transportation application. And we know now, 96% of hydrogen comes from fossil fuel. So as shown in this slide, we burn fossil fuel, coal, natural gas, and oil to produce hydrogen. It's not sustainable. And the main method is called steam methane reforming. That is a high temperature gas phase reaction. We can't rely on fossil fuel anymore. We must develop clean technology to produce hydrogen. So now we know people name hydrogen in different color, green, black, or blue. So this fossil fuel hydrogen we call black or gray hydrogen. And the blue hydrogen is, we capture the produced CO2 and to convert that one and to utilize, to reuse. So that process can turn the black hydrogen into blue hydrogen. And green hydrogen, and also you can see from BP's analysis report that shows the reserve to production ratio for the fossil fuel. As we can see within the next 150 years, we will use out all of the fossil fuel. So we must develop new technology. And showing here, if we use the electricity from renewables, from solar, from wind, we can use the excess electricity for water electrolyzer to produce hydrogen and also byproduct oxygen. This hydrogen can be green hydrogen. There is no emission of fossil fuel, no emission of CO2, no consumption of fossil fuel. And also the purity of hydrogen can be really high, more than 99.99%. Okay, so we know that for the water electrolyzer, there are three low temperature. If we consider all temperature range, there are 4 types. Traditional alkaline water electrolyzer, which is the mature technology over 150 years history. Second type is PEM, protein exchange membrane water electrolyzer. Third type is solid oxide water electrolyzer, which is high temperature process. Fourth type is IEM, ion exchange membrane water electrolyzer. That is my topic today. So for the PEM system, this is a mature technology. Its technology readiness level already up to 8 now, so it's commercially available. Now the challenge for PEM system is the cost. For any type of technology, if for massive production, we must make sure it's a cost effectiveness, otherwise it's meaningless. For the PEM system, rely on, because the system can feed in pure water. However, during the reaction at the surface of the electrode and the membrane, that is very acidic environment. pH is around 1 or 0. So at that high acidic environment, only precious metal, for example, platinum, palladium, iridium, ruthenium, are stable. Other metals just corrode. Without catalyst, reaction rate is very slow because the reaction is sluggish, kinetic very slow. So we must use the catalyst. Therefore, in the PEM system, rely on precious metal. I forgot to mention. For the PEM system, it's a mature technology, as I mentioned. Compared to traditional alkaline water electrolyzer system, PEM system have advantage of high efficiency, and the system can operate up to 1 amp per square centimeter operating current density, even can up to 2 amp per square centimeter. Now that some company claim up to 4 amp per square centimeter, the efficiency is very high, over 80%. For the traditional alkaline system, that is not for this system, that is zero gap system, so we can reduce ohmic drop significantly. Therefore, the system enable higher operating current. For the traditional alkaline system, that use the separate, not ion conductor membrane. So the distance between the electrode is large. So therefore, the maximum operating current is up to 300 milliamps per square centimeter. Therefore, PEM zero gap configuration enable us to operate high current and with the high efficiency. AEM technology combine the advantages of these two technologies. The system is operated in alkaline media. On the other hand, it's a zero gap configuration. That is the advantage borrowed from PEM system. So you can see with this system, we can use the cheaper metal because, for example, traditional metal, nickel, cobalt, iron are stable in alkaline media. So we can use this type of catalyst to speed up the reaction rate. And also, this is zero gap. We use the ion exchange membrane, which conducts hydroxide ion. So there is no gap. We call the zero gap configuration. The system ohmic drop can be reduced significantly. So we can reduce cost consequently. In the E2C project, as Soraya and my colleague already mentioned, in the E2C system, project, we use the PEM and PEM. We develop both technology. We use the PEM system for demonstration. And the project program encourage research. So in the WP1 that we call the enabling research, EU program encouraged us to develop low-cost ion exchange membrane that is target up to TRL level 3 to 5. So that is in the in E2C projects, in the second approach, we have two approaches. First approach is the direct convert of CO2 into chemicals such as formic acid or format. In the second approach, we call the indirect line. So in this process, we produce hydrogen first, and then we combine this hydrogen with CO2 to produce DME, as Soraya mentioned. So Exeter, we are in this indirect line. Our focus to develop low-cost ion exchange membrane water electrolyzer. I prepared a video. Let's see whether we can play it. If we can't, I just show very 2 minutes, explain the operation principles of the system, and it's easier to follow. There are some subtitles. Yes, you can read. In the middle is AEM, or anode, cathode, and in the middle is the membrane, which conduct hydroxide ion. it's very good video. I will share to you, and you can watch YouTube video. Very good explanation. And besides that is the gas diffusion layer that involve excellent engineering design. And we use the current collector stainless steel based material, and water feed in anode side, and reduction produce hydrogen. And hydroxide ion transports through the membrane towards the anode side, where it oxides to oxygen. In our demonstration, we showed dry cathode. In reality, in practice, there are many types of design. So not the focus today's topic. Okay, I stop sharing here. We can move forward. Yeah, so just to explain the operation principle of the AEM water electrolyzer. In the E2C project, our research focus, firstly, develop efficient catalysts for both oxygen evolution at anode side and catalyst for hydrogen evolution reaction at the cathode side, and then design and develop membrane electrode assembly, which we call the MEA, which is the heart of the electrolyzer cell. And then we design the full cell, scale up the cell from 10 square centimeter size electrode area up to 100 square centimeter. So that is our research focus. And we also use the computing modeling technique, DFT, to guide us identify efficient catalysts. Yeah, so here just to show you the mechanism of oxygen evolution reaction. In reality, the reaction very complicated, not just simply as showing the equation of water splitting. So all of this, for example, contribute to the overpotential of the reaction. So we need a catalyst to reduce this overpotential, therefore to have a higher efficiency. We have studied a number of catalysts, including unary, binary, and ternary transitional metal oxide, nickel-based mainly, for oxygen evolution. That is oxide, hydroxide, or vinyl perovskite type metal oxide, which are commonly reported efficient catalysts for OER reaction. At the cathode side, we studied nickel metal alloy-based material. For example, nickel molybdenum, nickel sulfide, which proved to be good catalyst for hydrogen evolution reaction. In the lab, we use a microelectrode setup to select and optimize the catalyst. Because for gas reaction, that is three-phase, involve gas, solid, and liquid. When gas produced, they create huge ohmic drop. So sometimes it's very difficult to use the common technique to compare the catalyst. Therefore, we design a microelectrode setup, enable us to do reliable comparison. So as shown here, this is the setup, and here showing the microelectrode, which is a very fine wire. It's about 25 micrometer diameter or 50 micrometer in diameter, filled in glass rod, and then machined, cut the surface and just that small area exposed in the electrolyte solution. We use this setup to enable us to get very reliable kinetic data for catalyst, for example, overpotential, Tafas loop, exchange current density, etc. So this parameter very important to select catalyst. Here, give you example the result of the catalyst for OER, oxygen evolution reaction. As you can see, with that setup, enable us to get the we need the power. For example, the ternary nickel iron cobalt give us very low overpotential at 100 milliamp per square centimeter and even higher current, 500 milliamp per square centimeter. So you can see we can reduce the overpotential very significantly. This is the example for cathode side hydrogen evolution reaction. Here, give you some example. You can see nickel molybdenum, for example, here give very low overpotential for hydrogen reaction. And then we scale up, from the microelectrode to large scale electrode area. We coat that catalyst on large piece of nickel mesh and then assemble in the cell. We use the commercial membrane. We use the Fumatech ion exchange membrane for our research. We also use the other commercial membrane for the comparison. So this is the data from cell after we assemble the cell. You can see this is the cell voltage as a function of time. And also we test the catalyst stability under different conditions in variety of operating temperature, concentration, and different operating current to see whether the catalyst is stable or not. As shown in this picture here, small cell, 10 square centimeter cell, and in the middle, that is 100 square centimeter cell. We closely collaborate with the TNO, and we pass our sample and the cell to TNO for further test, and then we get feedback, and then to optimize the cell. And you can see here now when operating the 4 amp kWh at half amp square centimeter, the cell voltage is 2.18 volts. And you can see there are still a lot of work ahead for us to further optimize catalyst and engineering design to improve the efficiency, to reduce the cell voltage further. This is more test results. Different condition, and also we have done dynamic load testing to mimic the practical condition operate in various currents. This is very preliminary result. We are writing the paper, haven't published the result, but the result is very promising. As you can see on the top, that is data without catalyst. You can see the cell degrade very quickly. We don't know now, it's difficult to get conclusion, it's due to membrane or due to catalyst. But under the identical condition, you can see with the catalyst, this red line figure quite stable compared to without catalyst, so which means catalyst does help extend the cycle life of the cell. Okay, come to conclusion. So zero gap water electrolyzer for hydrogen, we think it's very promising because it's a reduced cost. And from our research, we found the nickel iron cobalt hydroxide very good catalyst for oxygen evolution. And on the other hand, the nickel molybdenum alloy very good for hydrogen evolution. Currently in the lab, we've also studied nickel sulfide type catalyst for hydrogen evolution, which showed very promising results. And as shown in the previous slide, the PhD students carry on research on perovskite catalyst for oxygen evolution. We will have more results in the future. Stability test is very important. Sometimes catalyst activity is very good, but during the longer duration test, they degrade. So we usually test the sample for 10 days continuous operation, and also in the meantime, intermittent test to see the stability performance. Here I'd like to acknowledge the partner, particularly here in the the Adeline, Dr. Adeline here. She is a researcher working on catalyst development and cell design. Now she got a new job in Johnson Matthey, started from the earlier this year as a scientist in fuel cell department. Another researcher at the end, Dr. Habib Ulaha. He is a DFT expert to design the computational computing modeling simulation work. And also I'd like to acknowledge the partner Dieulot and the University of Lille in the collaboration in indirect line. That's all. Thank you very much.
For stability, thanks. First of all, thanks for the presentation. For stability, what kind of stress tests are you running? Like, what kind of range of potential are you stressing?
We didn't apply any pressure in our current cell. You are right, and we just operate in ambient.
Also, the applied potential, like you have like most likely a stationary potential. This is where the efficiency should be the highest. But to get the stability over longer time, usually, as you said, you're doing 10 days experiment. But they should like drive the hydrogen production for years, usually. So are you running like extreme stress tests to see how the cell will behave, or the cell is?
That's a good point. We haven't, in our lab, we haven't done that test. That is our collaboration with the team O. Continue to do this stress testing. That's a very good point. I don't have data today.
You also don't have any slides or.
Maybe
you're looking discuss later.
Yes.
To also show some things.
Yeah.
Maybe that accelerate stress test.
Accelerate stress test. That's a good point.
Thank you for it all. So one of the issues with anionic exchange members is crossover. I'm wondering, are you following iron on the other side of your catalyst? So on the other side of your membrane, are you following the metals that are dissolving on each from your catalyst over the membrane? Are they going on in zero gamma, or are they going across the gears?
That's very interesting. We haven't found any leaching or contamination of the catalyst through the membrane. We haven't, but we found Now the challenge on membrane is very big challenge, because membrane without KOH, membrane not working well. And also temperature, some limit up to 60 degrees. That is claimed from membrane supplier. So now we control temperature up to 60 degrees. If above 60 degrees, membrane degrade, not catalyst. We also operated at higher temperature, 80 degrees, for example. Catalysts seemed okay. Now the big problem comes from membrane. Yeah, but that's a very good point.
I think we have to stop there, but if there's further questions, please discuss during the lunch. Thank you, and also help me thank all the other speakers as well.